Okay, so for the domain and the range of a function, the domain are the x values or the inputs. And they can be found with the help of vertical boundary lines when you're looking at a graph. Oops. Hope if I spelled vertical right. Because these vertical lines represent the x value, so that's why the vertical line test works, because we're representing an x value. And then the range are the y values, or the outputs. And they can be found with the help of horizontal lines, because they represent the y values. So let's take a look at the graph of y is equal to x squared minus 3. And again, you can go through a t-table, figure out points to plot. I'm just going to list those out. Negative 3, 6, negative 2, 1, negative 1, negative 2, 0, negative 3, 1, negative 2, 2, 1, and negative 3, 6. And we know since this is a squared function, it's going to be a parabola. So let's plot those points. And it looks like it's symmetric with respect to the y-axis. So we can easily just put in the rest of our points, connect those together with a smooth curve in the shape of a parabola. Make sure you put arrows on the ends because this continues on forever and ever. So let's take a look at the boundary lines to help us determine domain and range. So first of all, we're going to look at the vertical lines for the domain. And let's just start somewhere. Okay, right here. So this is representing x is negative 1. And if you look, there are x values on either side, so this is not a boundary line. So let's go a little bit further over to the right. And again, you see that there are x values on either side of that vertical line, so we continue to go to the right. Now, you see that this boundary line does not cross our graph because our graph stops. We've reached the boundary of the grid. But with our arrows, we know that this line is going to continue to go out towards the right. Same thing happens over in the left. If we put a boundary line over here, we still have more values that are going to be continuing off into the left. So our domain for this particular function is x is an element of the interval from negative infinity to positive infinity. So it's all real numbers. So you can put in any value of x and get an output of y. Okay, let's take a look at our horizontal lines, which are representing our y. So I'm just going to arbitrarily put one in here. Let's do y is equal to 3. And you see that there are y values above and below. Let's go down because it looks like that's where we have a true boundary line, which happens to be right here at y is equal to negative 3. And you can see that I drew that in as a solid line because that is the point where all of our y values are above and there are no y values below. So that helps us determine our range, which is y is an element of the interval, and we're going to include negative 3, and then we're increasing forever, so that's positive infinity. Now, you don't really have to draw these boundary lines in. You can just kind of visualize what the boundary lines are going to do here. Now, when you don't have a graph, we have equations that have an implied domain. So an implied domain is a set of all real numbers for which the function represents a real number. So for rational expressions, these are the ones that are fractions. We want to exclude any inputs, any parts of the domain, any x's that cause a denominator of 0. And we've done this before in previous sections, so this is just a review. And for a square root expression, the domain excludes, exclude any input values that create a negative radicand. And remember, the radicand is the part under the radical. So key idea here is we want to include the zeros and the positive values. So let's take a look at some examples. So the first example, this is a rational expression. And here we want to say our denominator cannot equal 0. So this, we would say x plus 3 cannot equal 0. And then we solve that, so we know that x cannot equal negative 3. In interval notation, that would be x is an element of the interval from negative infinity to negative 3, union negative 3 to positive infinity. Our next example is a square root. So we know with the square root we want to exclude the negatives, but we want to include the positives and 0. So we're going to say 3x minus 2 is greater than or equal to 0. So we solve that, and we end up with x is greater than or equal to 2/3. In interval notation, x is an element of the interval from positive 2/3 with a square bracket to positive infinity with a parenthesis. Our last example is a polynomial. Now, polynomials do not have variables or any variables in the denominator, and we don't have any square roots in this one. So this would be no exclusions like the last ones. Oops. So our domain would be x is an element of the interval from negative infinity to positive infinity, which means all real numbers. So let's see what happens when we combine these properties or these exclusions together. So if we take a look at the next one, here we have a rational expression with a square root. So the rational expression, we know that the square root of 5x minus 6 cannot equal 0. And because that square root is in the denominator, we know that 5x minus 6 has to be greater than or equal to 0. Excuse me, it doesn't matter that it's in the denominator. It's just the radical has to be greater than or equal to 0. So we have an and statement. We need to take into account what is, or for both of them. So what we're going to do is combine them into 5x minus 6 is greater than 0. And that's the inequality that we're going to solve. So we solve that and we get x is greater than 6/5. We write x is an element of the interval, parenthesis, 6/5 to positive infinity, parentheses. The next one is similar. This has a square root with a rational expression. So here we need to make sure that the part under the square root, which is 3 divided by 7 minus x, is greater than or equal to 0. And that our denominator, 7 minus x, does not equal 0. Now, if you take a look at the rational expression, 3 is always going to be positive, so our numerator is always going to be positive. So really, the only thing we have to worry about is our denominator being positive or 0. So 7 minus x is greater than or equal to 0. So we're going to combine those together. This is very similar to the last one. And 7 minus x has to be greater than or equal to 0. And if we solve that, since we're subtracting 7 from both sides and then dividing by a negative, that's going to flip our inequality symbol. So our result is x is less than 7. Let me correct that. This should be 7 minus x is greater than 0, not equal, because we have an exclusion of equal because of the rational part of our function. So again, we solve that, we end up with x is less than 7 in an interval notation. X is an element of the interval from negative infinity to positive 7 with parentheses on both.